All right, another physical property of gases that we're going to take a look at is their temperature. So let's take a look at the temperature, units of temperature we've kind of used or are familiar with. We generally use degrees Celsius in science, and degrees Fahrenheit for us, Americans. However, what I'm going to say is that these units don't make sense, and I'll explain what I mean in a minute. Remember that temperature is a measure of thermal energy. Right, so they're measuring how much thermal energy our substances have. Let's think about some other measurements. For example, maybe mass, but it works with other stuff, length, volume, anything like that. If you have 0 grams of something, zero grams of stuff, you have nothing. Right, and similarly, if you have 5 grams of stuff and then you go to 10 grams of stuff, you've doubled the amount of stuff you have. So 0 in these kinds of measurements means nothing. What about 0 degrees Celsius or 0 degrees Fahrenheit? Do these two mean that we have 0 thermal energy? And the answer is no. They do not mean that we have 0 thermal energy. Thermal energy is corresponding to the movement of particles, and at 0 degrees Celsius or Fahrenheit, these particles are still moving around and vibrating. And you can think about it, we can go to negative degrees Celsius and Fahrenheit, maybe not here in California, but in other parts of the country, you get to negative temperatures pretty routinely in the winter. And that makes sense, it gets really cold, but like 0 or negative mass or negative volume, that doesn't really make sense. And then the same thing for the whole doubling idea. If you go from 10 degrees Celsius to 10 degrees Fahrenheit, and you kind of quote unquote double that to 20 degrees Celsius to 20 degrees Fahrenheit, have you doubled the thermal energy? And the answer is no, you have not. It's not even close. And so what's going on? Why do these kind of other units make sense while temperature doesn't make sense? Well, if we think about it, length, volume, mass, they're relatively easy to measure. Slash pick a 0. Right? What is 0 length? Well, it's no length. What is 0 mass? Well, it's no mass, right? You don't have anything there. 0 volume, you have no volume. But what about thermal energy? Thermal energy is not something that we can directly see. And so what does it mean to have 0 thermal energy, right? How does somebody pick that? And especially back in the day before they had all these advanced instruments, what does, 0 thermal energy mean? Well, in 0 thermal energy, everything would stop moving. All particles would have 0 motion because there's 0 thermal energy. And actually, it's actually impossible to reach this, as far as we know, because as you get lower and lower in temperature, we get some crazy quantum mechanics stuff going on. And so what do these zeros mean in terms of degrees Celsius and degrees Fahrenheit? Well, they were just arbitrarily chosen. Someone did something and they said, hey, I'm going to make this 0. With volume and mass, it's really easy to pick a 0. It means nothing. But with degrees Celsius and degrees Fahrenheit, it was just arbitrarily chosen. So for example, 0 degrees Celsius was chosen as the temperature at which water freezes. Right, so that's cool. I mean, it makes sense to pick that as your 0, but that doesn't mean that there's actually 0 thermal energy, right? It was just arbitrarily chosen. 0 degrees Fahrenheit, there's some contention about why this was actually chosen. The most popular one is that this is where salt water freezes. So someone made a really saturated saltwater solution and then got it really cold, and they saw that it froze at a certain temperature, and they said, I'm going to call this 0. And same thing, 100 degrees Celsius and degrees Fahrenheit was also arbitrarily chosen. And then you just kind of measure the units in between. For degrees Celsius, it makes sense to me, but that's when water boils. So that's kind of logical. Degrees Fahrenheit, it's approximately body temperature. So you can see, I don't know, in my opinion, degrees Celsius is a little bit more logical, but nonetheless, they're still arbitrary. And so if we want to do science, and if we want to talk about doubling the thermal energy or something like that, we need a real temperature scale where 0 actually means 0. And so scientists have figured this out. What does 0 actually mean? And then they gave this scale a name, and this is known as the Kelvin scale. And it gets the symbol K. And the cool thing about the Kelvin scale is that you don't have to include that little degrees symbol. So if you're ever typing anything out, it's easier to convert it to Kelvin. That way you don't have to find that little degrees symbol in Word or whatever program that you're using. And 0 Kelvin means real 0. There's 0 thermal energy. And again, that means that all these particles have no motion whatsoever. It's not actually possible to reach 0 degrees Kelvin. We've got to like very close to like micro Kelvin and that kind of stuff. But all kinds of crazy quantum mechanics stuff happens. In terms of converting, we're only going to focus on converting degrees Celsius to Kelvin because those are the two kind of science temperatures. And they're relatively easy to interconvert. Your Kelvin is going to be equal to your degrees Celsius plus 273.15. And you want to memorize this. So for example, if you had 25.00 degrees Celsius, you would plug that 25 in for this degree Celsius, and then you would convert it to Kelvin, and your Kelvin would be 298.15 Kelvin. Again, there's no degree symbol with the Kelvin. Note that because we're just adding a number, the delta T is the same for Kelvin and degrees Celsius. Right, so if you have a 5 degree Celsius or degree Kelvin difference, that's the same. They're both 5 units different, but the 0 is different, right? 0 Kelvin means actual 0 thermal energy. 0 Celsius means 273.15 Kelvin, and there's still, plenty of thermal energy. Here's just a little picture that compares the 3 scales, right? You've got Kelvin on the left, Celsius in the middle, and then Fahrenheit on the right. You can see absolute 0, right? All molecular motion stops. That's actually 0 Kelvin, negative 273.15 Celsius, and actually about negative 460 Fahrenheit. You can see water freezes at sea level at this temperature right there. There's your human body temperature, and then there's, water boiling and whatnot. And again, note that for Celsius and Kelvin, the increments are the same. So if you're using a delta T, you can use either value. If you're using just a T, you must use Kelvin. So in general, it's just easier to use Kelvin. So use Kelvin in problems. If you don't use Kelvin, you will get the problem wrong.